A very good morning to our lecturer, Dr. Sharu. We are from BMID, and today our group will present our industrial based CNC machining project, which is the track roller carriage. My name is Rogini, and together with my teammates, we will present the design, engineering concepts, and machining process involved in producing this component in this presentation. Let's begin with an introduction to our selected component. These slides introduce our target component, which is track roller carriage. The track roller carriage is an important support axle used in heavy-duty linear motion systems such as CNC gathers and warehouse automation system. Its main function is to provide smooth and stable movement while supporting heavy loads. There are three important features. First is the internal geometry, which includes the central block. This passage is designed to allow grease lubrication so that friction is reduced and the moving parts operate smoothly. Second is the auto geometry. The step proves accurate bearing seating and ensure proper alignment while preventing axial movement. Lastly, the mounting section contains precision grooves for snapping ring and O-rings. These grooves help secure the assembly and prevent vibration or unwanted movement during operation. Overall, every feature is designed to improve the performance, stability, and durability of the component. Before machining starts, a proper engineering drawing is needed. Let's see in this slide most three important foundations. First, orthographic projection, which converts the 3D model into 2D views with complete dimension for manufacturing. Second is datum and the work coordinate system. This set the reference point and machine zero position to ensure accurate machining. Third is geometry, dimension, and tolerance constraint, which define the tolerance and surface finish requirement to ensure the final component meets the required quality and precision. Together, these three elements ensure the CNC machining process is accurate and reliable.
Hi, Assalamualaikum. My name is Nur Ismahandi binti Rizali. My matric number is B14200016. Phase 1 covers raw material preparation, the open loop stage before automated control begins. First, the material is manually cut using a horizontal bandsaw, which introduces dimensional variations. A stock allowance is then added to compensate for these errors. Finally, the edges are squared and deburred to create accurate reference surface for proper machine setup.
Assalamualaikum and good day everyone. My name is Siti Nur Sofia binti Latif and my matrix number is B1424100002. After preparing the raw material, we move on to phase 2, Sinotron Digital Twin Integration. In this phase, we use Sinotron of Sinometric as a digital simulation platform to create a visual representation of the machining process before actual production. The first step was workpiece definition. The hand-saw raw material was mapped onto the simulator together with the required safety stock allowance. This ensured that enough material was available to remove the rough and uneven surface created during the manual cutting. Next was circle selection. We configure that appropriate shop mill conventionally machining circle, including facing, pocket, and contour circle based on the dimension and specification provided in the engineering drawing. This circle was used to define the machining strategy and tool movement need to produce the final component geometry. After the machining circle was configured, the program underwent simulation. A 3D visual simulator was performed to track the tool traction and verify the final dimension and detect possible collision between the cutting tools, workpiece, and clamping setup. This verification process helped minimize machining error and improve operational safety before moving to the actual CNC machining. As shown in the simulator, the complete machining sequence and component profile could be visualized before production. This digital twins approach allows us to validate the CNC program and confirm that the required geometry can be produced accurately. In summary, phase 2 serves as a verification stage that reduce the risk of the machining error, improve process reliability, and ensure that CNC program was ready for physical execution. After completing the simulation stage, we proceed to phase 3, physical lead execution, where the CNC program was transferred from the visual environment to the actual CNC lead machine. First is work holding and alignment. The raw material was loaded into the lead chuck and securely clamped. Since the stock was manually cut using a handsaw, careful alignment was required to minimize runout. A digital indicator was used to perform radial trim and ensure the workpiece was properly centered before machining began. Next is lead kinematic. Unlike milling, where the cutting tool was rotated, the lathe operate by rotating the workpiece at a high speed while the cutting tool remains stationary on the thread. As shown in the figure, the tool moves along the z-axis to control the length of the component and along the x-axis to control the diameter. Finally, we move on to the machining circle. We begin with the facing operation, which produces a flat and square reference surface by removing the uneven handsaw end face. Once a proper reference face was established, we perform rough turning using circle 95 to progressively remove excess material and form the required outer profile of the component. Although the machining process follows the program toolpath, several real-world factors influence the final result. This including variance in raw material, cutting force, variation, terminal effect, tool wear, and a small measurement error during inspection. This factor explains why the actual dimension different slightly from the simulation result. A dimensional accuracy metric showed that most critical dimension was very close to the target value. The central step profile achieved zero deviation, while the outer and second diameter only different by plus 0.01 mm and plus 0.05 mm respectively. The groove wave show a deviation of minus 0.30 mm and the largest arrow was found in the total component length with a deviation of plus 3.27 mm. Overall, the core dimension were maintained within the tight tolerance, demonstrating successful CNC machining performance. Although improvements are needed to reduce the length variation.
These slides highlight the main physical disturbance affecting machining accuracy. Uneven hand-sewn stock causes unstable cutting. While manual measurement can introduce setup errors, structural deflections may affect alignment under cutting forces, and heat generated during machining can cause thermal expansion and tool wear, reducing precision. This project successfully transformed the CAD design into a high-precision physical part. Sinetron simulation and shop mill programming accurately translate the digital model into machining operations. By using adaptive machining with cycle 95, the system compensates for errors in manual material preparation and achieve the required dimensional accuracy.